All right, now let's get into some complicated stuff. Let's get into an object sitting on a ramp. Now this problem right here, as I do it, is going to assume that you've had some notes already on how to know the force, the normal force, and the force up and down the surface of the ramp, parallel and perpendicular to it. So I'll just assume you know that at this point. So here's what I've got. I've got a 40 kilogram box sitting motionless on a ramp with a 35-degree angle. And it says, what is the force of friction necessary to hold it in place? Now, motionless again implies it isn't moving, which means it's not accelerating, which means all of my forces are in balance here. So I'm going to go ahead and put my box on here, 40 kilograms. And that means I'm going to have a force of weight down, and that's going to be completely vertical. And again, 40 kilograms, 10 meters per second squared, that's going to be 400 newtons. Now I'm really kind of just putting this here as a placeholder for now, and we're going to break it down into these other two forces. I've got a force that's going to be into the hill here, and I have a force that goes down the hill. And this force right here is going to be equal to the force of weight times sine of theta, or mg sine theta. So that's going to be 400 newtons times the sine of 35 degrees, and that's going to be 229 newtons. I'll go ahead and show that calculation on here. It's going to be 400 times sine of 35. So 229.4, we're just going to make it 229 for the purposes of this. Which means if that's the force down the ramp, that is also my force of friction up the ramp, 229 newtons. And boom, that's all there is to it. I don't even necessarily need to calculate the other portions of this thing. If they were to ask me about the coefficient of friction, then I would need my normal force, which would be perpendicular here. But because all I need is the force of friction, I just need the force down the ramp, and that's all we have to do for that problem.